Jambo. Welcome to today's resumption of physics lessons. And here we are going to have a discussion on the reflection at curved surfaces. May you subscribe, like, comment, you keep sharing, and may God bless you. We can start right away. So here, this is chapter 5 of physics from 1, from 2. It's a very interesting chapter, and it has some correlation with reflection on plane surfaces, but that is all about the laws of reflection. You can go straight to the introduction part of the chapter. So this is now the chapter. In this case, we're going to do or to deal straight with majorly two types of curved surfaces, and that is one, a concave, and a convex mirror. These will be the key areas of discussion for this chapter. Therefore, we can go further. So this is the concave, and this is the convex. But we shall look at it in a detail. So this is just part of the introduction, pictures of the introduction. Let's start with the concave reflector or the concave mirror. Curved surfaces may be obtained from hollow shapes of spheres, cones, or cylinders. When these surfaces are highly polished, they become reflectors. In a hollow metal sphere, for example, if the inner surface is highly polished, then the portion of the sphere is described as concave reflector or mirror. Conversely, if the outer surface is highly polished, then the portion of the sphere is described as convex. So, you can gauge on the polished surfaces. For a concave, we have said that if the outer surface, if the inner surface is highly polished, then the portion of the sphere becomes a concave reflector. So you can see the outer part is highly polished. So you can have a look on the diagram on the sides of where we have the polishment and the reflecting surfaces. Just a minute. I will follow up on the other side. So silvering of the inner surface of the glass produces a convex mirror, while highly polished inner surfaces gives a concave reflector. This one will be a very key interesting point. Let's look at the terms that are used. Uh, but before you look at that, let me uh, clearly show some of the key interest point to avoid confusion. So in case you're having a mirror like this, it is curved, and then this is the reflecting surface. Then this one becomes concave mirror. If on the other way around, this becomes the reflecting surface. Then this one becomes a convex mirror. That is something to clarify so as to ensure that there is no cause of alarm. Let's continue. Terms associated with curved reflectors. You can have this diagram, of course. It is a diagram that we are, for those who are already in Form 2 or past Form 2, they have already witnessed it. You can see we have talked about where we can get these mirrors or these reflecting surfaces just from hollow spheres. Here is C. Therefore, we have the center of the sphere and we have other parts of the sphere where we shall have key interest in. So if you pick this one to be an hollow sphere, then you can see in case we complete it, it will be a complete sphere. So at the center, it is called the center of curvature, while we have the middle part of where the mirror is, then it is called the pole. The same applies to a convex, but when it comes to issue of the sign convention, things will turn out to be different on where we should place the center of curvature and the radius of curvature. We may proceed to the definitions. So we'll start from here. For the concave mirror, the rays converge at point F. That is called the principal focus after reflection. For the convex mirror, the rays are reflected, so they all appear to diverge from the principal focus behind the mirror. Therefore, if you are asked to define what is the principal focus for both concave mirror and convex mirror, then these will be totally two different definitions, because one will be truly converging and the other one will appear like it is coming from that point. Therefore, if I may write this one for principal focus, I'll say for a concave mirror, for a concave is the point where all rays close and parallel to the principal axis. Do converge after reflection. But when it comes for a convex mirror, is the point where all rays close and parallel to the principal axis. Do appear to diverge after reflection. There is difference between do and do appear. Do and do appear. Let's get back to the notes. So if you pick the concave mirror, then this is the point that we are talking of, F. So all rays that are close and parallel, this and this, they are close and parallel. After hitting the reflecting surface, then they do converge at F. But when we are having convex, all rays close and parallel, the principal axis, then they appear. So the part appearing shall be using dotted line. So this one shall be using dotted line. We may proceed. We have the pole is the center of the mirror, P. So where is it placed? It is here. You're gonna have a better view. Then it is this part, P, a better view. Then it is that one. We have the next term. We have the center of curvature. Is the center of the sphere, of which the mirror is part. In the case of a concave mirror, the center of curvature is in front of the mirror, while for a convex, it is behind. How will that one happen? So we have this one for a concave mirror. We are saying that it is at the front part, but for this one, it is behind the mirror. That one will be clearly elaborated when it comes to the ray diagrams. Tutaonyesha hiyo vizuri sana. Let's continue. We have the principal axis. Is a line drawn through the pole of the mirror and the center of curvature. It's also called the main axis. The principal focus, we had already defined it. So this one is defined in terms of the concave and the convex. We have the focal plane is a perpendicular is a plane perpendicular to the principal axis and passes through the principal focus. Parallel rays, which are not parallel to the principal axis, would converge at this point on the focal plane. So maybe I can draw this one. So if I say that this is picking this one to be the concave mirror, and this one becoming my principal axis, then I say that this is my F and this is my C. Then now we can draw a perpendicular plane, this one. So this is F, this is C, and this is P. We have the radius of curvature. It is the radius of the sphere of which the mirror is part. In short, it is the distance from pole to the center of a curvature. So if you look at this diagram clearly, then the radius of curvature will be the distance from P to C, like that. That one will call it R, radius of curvature. We may still proceed. So you can say PC is giving us the radius of curvature. We have the focal length is the distance from the pole of the mirror to its principal focus. So focal length will be the distance from P to F. So this one becomes our F. So PF becomes our F. It is noted by a small f, like that. So if you look at this one, you'll finally realize that R is equals to 2F. That will be the final conclusion about the relationship between the two, radius of curvature and the focal length, F. We had already talked about the focal plane. It is a plane perpendicular to the principal axis and passes through the principal focus. I've already indicated it using dotted line in my previous diagram. You can see we are having some diagrams here. We do not have a need for them. Now we can move on to the laws of reflection in curved mirrors. We have the first law, which says that the angle of incidence is equal to the angle of reflection. The incident ray, the normal, and the reflected ray all lie on the same plane at the point of incidence. Mostly, people do forget about the laws of reflection, especially the second law, which will be stated as the incident, the normal, and the reflected ray all lie on the same plane at point of incidence. Lie on the same plane at point of incidence. Then the other one is the incident angle will be equal to the reflected angle. I is equals to R. In this case, you will say that all these one are also applicable to reflection on plane surfaces. It's also applicable to reflection on plane surfaces. This one is demonstrated by diagrams, that is A and B. So this is for a concave mirror, and this one is for a convex mirror. The moment we say they lie on the same plane, this is the point of incidence that we are talking of. So yeah, that is the point of incidence. Because we have this part which is practical, we may not cover it now because it requires the real working from the lab. Ray diagrams, here we have. So ray diagrams can be used to explain how images are formed by curved mirrors and the characteristics of these images. The reflecting surface is represented by a straight line and a small curve. And a small curve is used to show the type of mirror. So for example, if we have this one, this is for concave and this is for convex. We may stop at that. Then in the second session, maybe we shall start with the ray diagrams. We have some interruption from the rains, therefore there will be some noise around. The rains are still predictable. You can start with the ray diagrams. You can continue actually. Then there are some rules that do govern us the moment we are looking at array diagrams. And we have number one, array that is close and parallel to the principal axis converge at F for concave appear to diverge from F for a convex mirror. We have number two, a ray that is passing through the center of curvature is reflected back on the same path. And this is due to a certain principle called the principle of reversibility of light. So through the principle of reversibility, reversibility of light. And this principle states that a ray light will follow exactly the same path if its direction is reversed. So those are two major, two main rays that we consider during the drawing of ray diagrams. We can add others, but these ones are minor. When we observe that init angle is equals to the reflected angle. So this is for a ray that is at a certain angle to the reflecting surface. Uh, may start. So this one you can say array at angle. So it will observe this rule. Then now we can start with the array diagrams. And this one will do with image formation and the characteristics. So we can have image formation and characteristics. So for the first case, we shall be considering on concave mirror. Then now we shall start with the first one, which is when an object is at infinity, that will be our first one. Then we may start. So I'll just give a pick my concave mirror this manner. Then I will indicate the sign. So this is shaded parts, and this is the reflecting surface. Then I can now identify my F. Probably if I say it is 5 centimeters, then our C will be at 10 centimeters from P. So this is our C. This is our F. Then now I will do that. I'll introduce some parallel rays. So that we can show that they are coming from infinity. Like that. Then this one is at an angle like that. So this one will be an incident ray. Then it emerges in that manner. So mine might not be to accuracy because we need it to be accurately drawn so that you can get the correct figure. Then may introduce another ray. And this ray now is parallel to the first ray. Like that. It is a ray that is at an angle. So we have said that if you have to draw it, then make sure that the incident angle is equal to the reflected angle. So if you accurately draw them as per those rules, then the two will merge at F, like that. The two will merge at F. Then I will introduce my image in this manner. So this one becomes my image. This one is from infinity. Then we can derive the properties of the image forms. We can say first, number one, from the position where it has been formed, which is image formed at F. Number two, allow me try to magnify it. So that you can see it clearly. So these parts, like that, then you can show that I have given an arrow pointing downwards. Therefore, this means that the image is inverted. You can say upside down. We can have the other one. Any image that is formed in front of a concave mirror, then we say that it is real. And then from our imagination, from where it was coming from, then the one that we have got will be smaller than the object. And in this case, we can say that the image formed is diminished. It is diminished. We may now look at another one, a second part. And this is when we have the objects beyond C. That is objects beyond the center of curvature. So in this case, I'll prepare my Sorry. So this will be my mirror. Then I'll show my principal axis in this manner. Then probably I'll say that my focal length to be about 1.5 centimeters, or maybe I say 2 centimeters. So in this case, allow me say that my F is 2 centimeters, meaning that my R will be twice, which will be the same as 4 centimeters. Therefore, I can take my ruler and measure that this is 2 centimeters from the pole, and here we can have our C. Therefore, now I can draw my C at these points and my F at that point. This becomes my F, my C. Then now we are told an object that is beyond C, beyond C. Therefore, maybe I can project that this becomes my image, sorry, my object. Maybe you can give it its own height. This one is 1.5 centimeters. Let me draw the tip that may be clearly visible. That way, I label it O because it has become my object. Then I will use the rules that we shared, that the first ray, that is the ray that is close and parallel, and this ray must be touching the tip of the object. Then for a concave mirror, that ray will be reflected through F. Here we go. So this becomes my first ray. A ray that is close and parallel, the principal axis, and also touching the tip of the object in this manner. We are saying that this one will be reflected through F. You must always show the ray direction. Then my reflection at F will be like this. This is now my reflected ray. You also indicate its direction like that. Then now we can use a second ray, which is a ray of light passing through the center of curvature C. And in this case, we have said that through the principle of reversibility of light, then that ray will be reflected through the same path. Therefore, as it passes through C, then it must also be touching the tip of the object. Therefore, this is what is coming out now. Like that. Then you must show the ray direction that it was coming from the object, like that. And upon hitting the reflecting surface, it was reflected through the same path, like that. I usually say that it is okay to draw this. This one will be very much okay. But if you draw like this, I'll give you a wrong. So choose wisely on which ray path for this ray that is passing through the center of curvature. Then now, these two rays have met somewhere, and this is where we shall be drawing our image. Therefore, you draw it carefully. Like that. Then it is having its arrow pointing down. Therefore, we can say characteristics for this one. From the position where it has been formed, it is formed between C and F. Number two, it appears or it is smaller than the object, so we can say it is diminished. If you look at it, it is formed in front of the mirror, so it is real. And then the last one, it is pointing the other way around, so we can say it is inverted, like that. We may now proceed to another positioning of the objects, and these will be objects at C. This one will be object at C. Objects at C. This one appears to be somehow tricky. But we shall manage. Therefore, allow me present the ray. So let me check how many centimeters should I draw. Probably 2. for the principal focus or the focal length. So if this becomes my F at 2 centimeters, it means that at 4 centimeters will be my C. Just a minute. So now we can continue. That is my C. This is my F. And we are saying that we want an object that is at F. We can draw it probably up to these heights. A height of 2 centimeters, maybe. Maybe I use a different color so that it can be feasible. This is now my object O. Then we apply the first law. Sorry, the first ray, that is a ray that is close and parallel to the principal axis. We said that this one will be reflected through F. So that is the ray now. Like that. Don't forget to show the ray direction. Like that. Then now, from the principle of reversibility of light, if we use the second ray, that is a ray that is passing through the center of curvature, it may confuse many people. And therefore, now let's apply the principle of reversibility of light, and then we transverse or we reverse the ray that is always close and parallel to the principal axis. So if it is reflected through F, then now we can start with a ray that is going through F. It will be reflected in a parallel manner. So maybe I can show. So if we say that this is a ray that was close and parallel to the principal axis was in this manner, what about if we change, we say that we had a ray that was like this towards the reflecting surface, then it is reflected in a parallel manner like this. How will it look like? Then let me use a different shading. So allow me extend this. That now we say a ray that was touching the tip of the object in this manner, and it went through F. Then it was reflected in a parallel manner like that. It was reflected in a parallel manner like that. We can repeat that ray. So this was the ray. Yes, like that. So that is how it was incident, and this is the way it was reflected back. Then now we'll have an image my reflected ray may not have been drawn accurately. But that is the point where they were supposed to be meeting at. Yeah, like that. So this is now my image. This one is always challenging because of matters to do with accuracy. Therefore, we can start deducing or showing the characteristics. Characteristics or the properties. Number one, it is formed still at C, sorry. If you compare the sizes, and then because it is in front of the mirror, then we can say it's still real. We may now look at object between C and F. before we start concluding the ray diagrams. Then finally, we'll touch on the special, the only and the only special. So that one was Roman 3. And now we can go to Roman 4. An object between C and F. So that is now my mirror. Always make sure that this one is at right angles. This part is at right angles or it is perpendicular. Then now I'll look at my F, where in this case I can still say use 2 centimeters. So that my C becomes 4 centimeters. Like that. So this is F, this is C. Then now we are talking an object between C and F. So if we place that object exactly at the center, like that, then we label it O. Then now we'll apply the first rays. A ray that is close and parallel. Like that. Always show direction before you forget. Will be reflected through F. It is healthy to always extend the rays. That is my direction. Then I'll have the second ray, which is a ray passing through the center of curvature. This one will also be touching the tip of the object. So this is the way to go. You have said that it will be reflected back in the same path, that manner. So this is where let me check something here. So I love my image in this manner. Always make sure that from this side it is perpendicular. Allow me show the tip using a different color. Like that. Then this one becomes my image. Then now we can start deducing on the properties of the image formed. Therefore, we have the first one from where it is formed. It is formed beyond C. Number two, if you look at it, you compare it with the object, it is larger. So we can say it is magnified, or it is larger than object. Then the next one, it is formed in front of the mirror. This qualifies it to be a real image. And the last one we have, it is inverted. So for the four scenarios, we can say that most of the images formed are inverted. Most of the images formed are inverted. Now let's look at object at F. This is the fifth case. So can I represent this one? So this is my F, my C. Then we are talking of an object that is at F. Like this. Then we are going to use two rays, the one that is close on the parallel and the one that is passing through C. Therefore, the one that is passing through, that is close on the parallel, will be reflected back. in that manner. The 1 through C. Like that. So if you compare this one, the reflected rays, they are just parallel. Therefore, we say this one is to infinity. So the objects, the image will be formed at infinity in that manner. The image will be formed at infinity. Let's look at the last special case. Last special case about the concave mirrors. And this is object between F and P. These are special parts because we expect to go the other way around, opposite of what we have been seeing. Therefore, I'll draw the principal axis. This is my F, my C, and this is my P. Very important. And now I draw an object in between F and P. Cell. Like that. So this is my O objects. I'll go by the first ray, a ray that is close and parallel to the principal axis. It will be reflected back through F. Like that. Then I will extend on behind the mirror using a dotted line like this. Then I'll use the second ray, which is a ray passing through the center of curvature. I'll still extend it to behind the mirror, but behind the mirror it will be in a dotted manner. So you can say these two rays I've just met somewhere. Yeah. Then this becomes my image. So this is the special case that we are talking about, because it is now for our first time that we have seen a concave mirror forming something that is an image that is erect. So characteristics, we may say image is erect. Number two, it is magnified. Number three, it is formed behind the mirror. And in this case, we say it is virtual. Then the last one, now we may not add another one, because if we start giving the position where it is formed, then it will be represented by the term virtual. So all this is all about the 6 positioning of images for a concave mirror. You have seen for the 5 cases, all images that are formed are real, but this becomes the only special case, and it is the one that tricks students. It is a special case. Under which condition does a concave mirror, so am I right, the question? And which conditions does a mirror, a concave mirror form an erect, magnified, and virtual image? When the object is between F and P, period. We can now take a look the last part to do with convex mirrors, and in this case we shall look at what we call the convention, especially in terms of the rays. Therefore, by convention, four lines represent real rays and objects. Dotted lines represent virtual rays and images. So let's look at a single case when it comes to convex mirror. Convex mirrors, no matter the positioning of the objects, they will always form diminished images. Therefore, this is now my convex mirror. This is the reflecting surface. Therefore, we say that the F and C will be virtual, or they will be behind the mirror. So this is my F, and this is my C. You can say probably we are having objects like this one. Then we'll use the first array, a ray that is close and parallel to the principal axis. This ray will appear to diverge from F. Like that, indicate the ray direction that manner. The second ray is a ray that is passing through the center of curvature, and I said it must always touch the tip of the object. Imefutika yote bana. Yeah, like that. Then the two rays have met somewhere here. Then that is where I'm going to draw my image like that. So I'll indicate the ray direction in this manner. Then I'll say that image is diminished and then it is virtual. So regardless of where it is placed, the object is placed, then this will be the scenario for these convex mirrors. Therefore, in our next session, we shall look at something else, maybe something to do with the linear magnification. So let's tune once we get the link. Thank you so much. Subscribe and share with your friends.